All right, I'm going to get started again. So want to cover a few things today. First, just kind of quickly talk through the data management lecture, and just the goal here is, again, like, you've already watched the lecture, hopefully. Yeah. Okay. A lot of nodding, so that's good. So the idea is just to give you a really quick review and give you a chance to ask any questions that weren't asked in the lecture that we recorded. And then, since we have a little bit of extra time today, because we lost one of our speakers, there's a fun project, a labeling challenge, and I'll tell you more about that when we get to it. And then we'll just talk quickly about what we're hoping that you get done on your projects for the next week. And then finally, we're hoping to have a few minutes left at the end to just for everyone to meet with their teams, and if you're still looking for teammates, to spend a little bit of time on finalizing that. Okay, so again, reviewing the data management lecture. I think Sergey motivated this really well. If you're a machine learning engineer, then there's a really good chance that you prefer thinking about models than you do thinking about data, because it's like kind of natural, right? Like, models are exciting, but it turns out in the real world that collecting data is super hard, and it can be really interesting, and it's actually more important than models. So I like this slide from Andrej Karpathy, the amount of sleep lost over models versus data sets. During the PhD, it's like all models, all models all the time. And then at Tesla, it's like 75% data, right? So even one of the best people in the world at thinking about models is now spending all this time thinking about data because it's that important. And so, why is it so important? Well, most deep learning applications just require tons of labeled data. And there are some branches of deep learning, like reinforcement learning or generative adversarial nets, that don't require lots of labeled data, but they're not really in the realm of practical, real-world machine learning yet. So you can also use publicly available data sets where you can get a bunch of labeled data for free, but the problem there is if you're only training on publicly labeled data sets, we talked a little bit about this last time, it's hard to really have a competitive advantage because everyone is kind of mining these for insights. They can be a good starting point, though. And so in the lecture, Sergey talked about a few things. He talked about data labeling, data storage, so where do your images go, where does your metadata go? Data versioning, so how to make sure that you are keeping track of which version of your data set that you're using to train your model at any given time, so you can always go back. And then data workflow, so like how do you put this together on a day-to-day basis and create a workflow that allows you to build new data sets rapidly and repeatably. I think the conclusions that Sergey made on data labeling were just, there's a bunch of different ways that you can do labeling. You can do it in-house, you can outsource it, or something else. But the conclusion was that if you can, you should outsource it, because this is sort of a difficult process, and it makes sense to have a specialist do it. And if you can't outsource it for whatever reason, it's too expensive, then at least use some off-the-shelf software. And if you're going to do that, then it makes more sense to hire people part-time rather than trying to, rather than trying to go do things manually on Amazon Turk yourself, it might make sense to just hire people part-time so that you can train them and have the same people that are doing your task over and over again. Were there any questions on what Sergey covered on data labeling? Data versioning? Yeah, I'll talk about that in a second, yeah. Okay. Mm-hmm.
So are some of these from the perspective of managing, managing a big project, or even for how does it translate to a small project like something we will be doing?
Yeah.
Which of those points do you think are the most important?
Mm-hmm. How many of you are planning to collect some data for your projects? Okay, so more than half, right? So I'd say all of this still applies. It's I think if you're running a really big machine learning project like a self-driving car team, then I think the percentage of time that you spend thinking about this goes up and up and up. If you're just doing a 6-week side project, then hopefully you won't need to spend more than a third or half of your time really thinking about data, because you're just trying to make a proof of concept. But I think it's still important to think about.
As a follow-up, can I ask another question?
Yeah.
So for a bigger team, do you think, will there be specialist teams which are just doing the data management kind of roles, or do you see the machine learning or AI engineer also doing all of these?
Yeah. So at some point, it makes sense to split the roles. I think in a small organization, a lot of times you see people who are like data scientists or even machine learning engineers that do all of the data management, all of the data munging, and all of the training, because there are just only a few people working on it, and so you need to do everything. A model that a lot of startups that I've talked to like is to have, at some point when the team gets big enough to have a separate data engineer, but to have that person sit on the machine learning team. So not have it actually be a separate team, but just have it be a separate person who works directly with the machine learning team, so that they're like in all of the conversations around what is needed from the model building process. Bigger organizations, I mean, at some point, it seems like most companies split off data engineering into its own function.
Yeah, I've interviewed with a company that has ground truth teams. So
Yeah. Yeah, and then labeling teams that's an entirely separate topic. And yeah, some companies just have many people that are essentially full-time employees that are working on labeling data. Mm-hmm.
So for a small project like Word, how would you structure your efforts? Which things are easier to get and which should be done first?
Yeah, I would definitely start with data, particularly if you want to collect your own data set, right? If you're gonna, and we are starting with data this week. So if you're gonna be able to use entirely or mostly off-the-shelf data, then I wouldn't spend too much time thinking about it up front. I would just go and create an initial version of the data set and start working with it. But if you need to collect a data set, then the usual advice of like starting small and getting everything working end-to-end first, there's a big caveat to that, which is that labeling a big data set takes a lot of lead time, because they're usually you have to do a bunch of different iterations. So it's something to start thinking about early. All right. I want to cover a couple of advanced topics in data labeling that were not in the lecture. So data labeling, as we've seen, is a really active and exciting research area. And there are a few directions that I think are really promising. Some are around how do you make the labeling process itself more efficient. One idea there is weak supervision, like Snorkel, which we just heard a lot about. There's another from Jeremy Howard. It's now a company called Platform.ai. How many people have seen this? Okay, great. I'm going to show you a video of Jeremy Howard talking about this.
So here we're starting with about 1.5 million car images, and I want to create something that can split them into the angle of the photo that's being taken. So these images are entirely unlabeled, so I have to start from scratch. With our deep learning algorithm, it can automatically identify areas of structure in these images. So the nice thing is that the human and the computer can now work together. So the human, as you can see here, is telling the computer about areas of interest, which it wants the computer then to try and use to improve its algorithm. Now these deep learning systems actually are in 16,000 dimensional space. So you can see here the computer rotating this through that space, trying to find new areas of structure. And when it does so successfully, the human who's driving it can then point out the areas that are interesting. So here the computer has successfully found areas of, for example, angles. So as we go through this process, we're actually telling the computer more and more about the kinds of structures we're looking for. You can imagine in a diagnostic test, this would be a pathologist identifying areas of ptosis, for example, or a radiologist indicating potentially troublesome nodules. And sometimes it can be difficult for the algorithm. In this case, it's got kind of confused. The fronts and the backs of the cards are all mixed up. So here we have to be a bit more careful, manually selecting these fronts as opposed to the backs, and then telling the computer that this is a type of group that we're interested in. So we do that for a while, we skip over a little bit, and then we train a machine learning algorithm based on these couple of hundred things, and we hope that it's got a lot better. You can see it's now started to fade some of these pictures out, showing us that it already is recognizing how to understand some of these itself. We can then use this concept of similar images. And using similar images, you can now see the computer at this point is able to entirely find just the fronts of cars. And so at this point, the human can tell the computer, okay, yes, you've done a good job of that. Sometimes, of course, even at this point, it's still difficult to separate out groups. In this case, even after we let the computer try and rotate this for a while, we still find that the left sides and the right sides pictures are all mixed up together. So we can again give the computer some hints, and we say, okay, try and find a projection that separates out the left sides and the right sides as much as possible using this deep learning algorithm. And giving it that hint, okay, it's been successful. It's managed to find a way of thinking about these objects that separated out these together. So you get the idea here. This is a case not where the computer is being replaced by a machine. The human is being replaced by a computer, but where they're working together. What we're doing here is we're replacing something that used to take a team of 5 or 6 people about 7 years, and replacing it with something that takes 15 minutes for one person acting alone. So this process takes about 4 or 5 iterations. You can see we now have 62% of our 1.5 billion images classified correctly. And at this point, we can start to quite quickly grab whole big sections, check through them to make sure that there's no mistakes. Where there are mistakes, we can let the computer know about them. And using this kind of process groups, we're now up to an 80% success rate in classifying the 1.5 million images. At this point, it's just a case of finding the small number that aren't classified correctly and trying to understand why. And using that approach, by 15 minutes, we get to 97% classification.
All right, so that's another kind of approach to this problem of how can we reduce the manual effort that it takes to label a big data set that I really like. And the reason I like it so much is because I think it's just a clever way of combining sort of what we do naturally when we're training deep learning models, which is kind of try to look at examples and build intuition about why the model is not doing well in these examples when it is doing well in these other examples, but then encoding that as part of the training process. Yeah?
So, do you know what's at the back end of this? Is it like just a deep learning or is it unsupervised learning?
Yeah, I'm not an expert on this, but my understanding from watching this video and talking to Jeremy about it is that they're training a classifier and then they're using features of that classifier in kind of an unsupervised way to do nearest neighbors. So you label a bunch of images, like let's say you label a handful of images, train a classifier on those images, and then you can use the features of that classifier to click on an image and then find the most similar images according to that classifier. And then once you found those similar images, then you can, it makes it easier for you to select those and label them all in a group. Okay. But in addition to figuring out ways to reduce the manual effort in labeling, there's also some interesting efforts in how to make the labeling process more accurate, right? So like I think when people think about labeling with crowdsourced labeling with Amazon Turk or something like that, sort of the default belief is like you have to make things really dead simple, otherwise you're going to get garbage results. And if you if you want to get things that are accurate on sort of like complicated, not yes or no questions, then it's really hard and maybe even impossible. I think that intuition is still pretty valid, but there's a couple of things that can make that better. One is label quality control. And so I'm going to skip this because this is what we'll talk about in the lab that we'll do in a few minutes. And then the other thing I want to mention is this Soylent paper. How many people have seen this from Stanford? Yeah, one person. Okay. This is a really fun paper. So the idea here was like they wanted to do this really hard task using crowdsourcing. And the task is to take a paragraph of text, and they had a couple of other tasks, but this one is to take a paragraph of text and make that paragraph shorter without changing the meaning. Right. So this is a unstructured task, and if you just ask people, random people on Amazon Turk to do it, they're not going to do a very good job because it's not very structured. And so what they came up with is a system that breaks this task into a bunch of subtasks, each one of which is pretty easy. And the way that they define it is a find, fix, verify loop. And so the way it works is instead of having one task, like summarize this paragraph of text, there's 3 tasks. The first one is to find, and so in this example, it would be like find parts of the text that can be shortened without changing the meaning. And so a bunch of labelers will find parts of text that can be shortened. And then there's fix. And so then in fix, the labelers get the output of the previous step. So they get the parts of text that some other labeler said can be shortened, and then their job is to shorten them. So it's a much more constrained task because it's just this single kind of block of text. They know they're supposed to shorten this. And then finally, verify. And this part is just looking at the results of the last step, and there's kind of an interface where the labelers can say, which one of these changed the meaning, and which one of these didn't actually make it shorter. And so they can sort of start to eliminate the bad results from the previous step. And so with these 3 things together, they're able to get kind of very good results for about, I think it was about $3 per paragraph, and sort of order of magnitude of minutes for each paragraph. Any other questions on data labeling? Yeah.
These methods used in a big organization for a real project?
I'm not familiar with whether big organizations have used this. Yeah, this is an idea I'm excited about, and I think it's an idea that's like very underutilized in machine learning right now. I think there are a bunch of types of data that are really hard to label right now, like 3-dimensional data for robotics that you could potentially be able to label with an approach like this. Okay, so moving on to data storage. Again, the idea here was that there's different ways of storing types of data. You can store it as an object in something like S3. You can store it in a database for things like metadata. If the data is totally unstructured, then you can just dump it in a big data lake and then aggregate it later. And at training time, everything needs to be locally on your file system. So kind of just core concepts here of how to store data. The more interesting part here, I think, is data versioning. And so Sergey kind of laid out the 3 or 4, I guess, different levels of how organizations approach data versioning. Level zero being, what most people are doing when they train machine learning models, which is just you have a data set and you train the model on that data set, and you have no way of tracking whether it's changed. Version 1 being, every time you train a model on a data set, you snapshot that data and save it so that you can always go back to that specific data set. And then version 2, which is the one that Sergey and I really like, which is versioning data as a mix of assets and code. Meaning, if you have like a database that has all of your metadata, then one entry in that database for each row is also a link to the bigger file that's stored in asset storage. It sounded like there's some questions on this piece of it. Yeah.
So on level 2, how do you think of adding new entries to this database, and how do you think of making sure that properties of the data set still maintain? Like, let's say you have a cat, and somehow you get a tiger. How do you make sure that that's a tiger and it doesn't screw up the rest of the data set?
Yeah, it's a good question. So I think, so if I'm understanding correctly, you're asking like, how do you have to, when you design a data set, you have to specify some sort of API for that data set. And then how do you deal with that API being broken by adding types of data that, like, for example, have a label that's not in your original scheme?
Yes, and more like breaking the scheme itself.
Mm-hmm. Yeah, I think like there's no real easy way around that. I think probably the way to do it is to sort of enforce it upstream using tests. So you have a test that says like, does anything in your data set break the scheme? And then you make sure that test has to pass before you can commit. And then sometimes you will have to break that. You will have to break that backward compatibility. And so that's just kind of a decision that you have to make very consciously, I think. Yeah.
Much more basic question. So besides having the sort of the regression, what's the point of doing this versioning for, right? I mean, if I just keep adding to the data set,
Mm-hmm.
besides the fact that I get a sort of a regression control, I can go back and look at, okay, when I trained this model, it was still good. What's the real benefit that's coming from?
The main benefit is exactly what you said, which is, a lot of times, a lot of times what you see, I mean, in software engineering in general, but like particularly in machine learning, is you change part of your code base and your performance gets way worse, and you just have no idea why. And it's super important to be able to catch those things early and revert quickly when that happens, because otherwise, you can like before we started being really careful about testing at OpenAI, we would have times when we would go like 3 weeks without training a particular type of model, and then we would train that model after 3 weeks and it wouldn't work, and then it's like you have 3 weeks of people's commits in the code base that you have to like try to somehow sift through to figure out where things broke, and if the breaking change happened earlier, then you still want all the good things that happened after that, and so it gets really messy. And so it's just a good software engineering practice to be able to catch things early and revert.
I mean, so that's on the code side of things, right? But on the data side of things, if I just keep adding to the data set, is there still an issue? And what's the issue that comes from just keep adding to the data set?
Yeah. So the way I think about it is machine learning models are code plus data, right? So the data is actually part of the code in some sense. And so to be really concrete, things that can happen are like, let's say that you have you added a bunch of things to the data set, but your labeler was like your best labeler was on vacation, and you have a bunch of messy labels that get added, and then all of a sudden you train a new model overnight, and that model is confused because it's been looking at a lot of bad data. You want to be able to revert that back.
Can you talk about the level 2, the mix of assets and code? What is the assets part?
Sorry?
Mix of assets and code.
Yeah.
What is that assets part?
Yeah, this was covered in the lecture. The assets are things like S3 blobs. Yep.
So when the assets are stored in multiple places, like some in S3, some in some database, doesn't cause a lot of network traffic to pull in all of them just during the training, and you might be training multiple models at the same time as well.
Yep. So I haven't in practice seen this be a problem. Yeah. I think in fact you can you don't really have to worry so much about bandwidth on the S3 side. But you definitely have to worry about it on locally. And so I think usually what people will do is they don't actually download the data from asset storage every single time. They have it backed up in asset storage, and then they just download a diff. So you're not actually downloading that much data.
I see. Is that automated, or you have to write your own scripts?
We write our own scripts. There's probably a better way of automating it. Yeah. I'll take one more question on this, and then I really want to move on. Yeah.
So are you running those tests on every commit to the data set, or nightly, or like weekly?
Yeah, we'll talk more about testing later in the class, but there are tests that run, I think like the best practice here is there are some tests that you want to pass every single time you commit to the code base, but there are some tests that you still really need to run that can't be run fast enough to do that, right? So like if you are training vision models, right, maybe it takes 12 hours to train your vision model, and it's still super important to make sure that you have a test that so that your ability to train those vision models doesn't regress. But it doesn't make sense to do that every single time you commit, because then it would just take too long to merge commits. And so then there's kind of a separate set of tests that you maybe run every night or every week or something like that. So you can still catch things pretty fast. Cool. Last topic was data workflows. And so the example was if we're training a popularity predictor, there's a bunch of different components of that data. So you have metadata, you have some user data, and some classifier data. And these are stored in different places. So in databases or in logs, or there may be the output of a model. And so the key idea here is like you can manage all these dependencies like every time you create your data set using something like a makefile, but it doesn't really scale all that well. And so there's these tools like Airflow, where you can kind of manage the dependencies of your data set creation process as a directed acyclic graph, and kind of run everything in sort of a more parallel way. Cool. All right. Up next, we have the labeling challenge. So this is the reason why I asked everyone to bring their laptops today. So what I'm going to have you do is just everyone kind of get together in groups of 2 or 3, with the people around you, and go to this URL, and it'll have instructions there for how to get started. And we'll spend about we'll spend about 30 minutes on this, and so we'll just see how far we get, and then we'll regroup after that. So let's discuss this. How many were able to run the baseline? Okay, that's really good. And how many people were just installing PyM the whole time? Yeah, I guess I hadn't anticipated that, but I probably should have. Part of your homework for next week is going to be to install PyM and make sure you can get it to work. All right, and how many were able to try your own thing and actually run it on the data set? Okay, a couple. Good. I think probably within another 15 or 20 minutes, it would have been a much higher percentage of people. So what I want to talk about is just what are the ideas that you had, right? So the challenge was we had this kind of method of getting labels from a bunch of labelers who had solved the same problem, which was just have them vote. And if greater than 50% of them said that this is the label, then we say it's the label, right? So what are some ideas of how we can do better than that? Yeah.
Probably the simplest I could think was have a worker score off and they are in the majority.
Yeah. So we can score workers. And how can you do that?
I mean, so just the basic was off and they are in the majority.
What else?
We're just going to weight them by the average 7-day accuracy.
Yeah, 7-day accuracy. What's the issue with that, though?
It's almost all the same.
Yeah, it's almost all the same. And then also, this is sort of I think maybe a particular of Amazon Turk, but when they show those 7-day accuracies, that's on all tasks, right? And so we might want something that's more specific to our task. How else can we score the workers? Yeah.
Just ignore all the workers who've done only less than 5 tasks.
Yeah, so we can ignore infrequent. Yep. How else can we eliminate workers that we don't think are good?
All the same answer.
Sorry?
All the same answer.
Yeah, all the same. What else? Maybe something that requires a little bit more work on our end.
They're judging too fast.
Yeah, the speed that they're judging. I think that's reasonable. Yep.
I'm not sure how to like it is. Out of 1 to 11 answers, we have the ground truth. We can check, how many of the answers are in the ground truth.
Yeah. Yeah, I think this is the key idea here, which is what you can do is you can have some of the answers where you know what the ground truth is, right? So in this, if you got a chance to look at the hints, then one of the hints was columns 11 through 15 are actually they're not being used to compute the to score how well our method is doing because we actually know what the ground truth is for all of those. And so when we set up the survey, we knew that 11 through 15 were always true and 16 was always false. And so one thing that we can do is we can look at how the workers are doing on those questions, and we can weight them based on that. So those are all ways of thinking about how to figure out who our best workers are. I think there's some others, but once we know who the best workers are, then we need to figure out how to combine them. And there are different ways of doing that. So let's say that we have some score for how good workers are, how can we use that score to combine what the workers said? Yeah.
Simplest is either you weigh them by the score or have a threshold. Below the threshold, you completely discard.
Yep, you can have a weighted average or you can have a threshold. I think those are both very reasonable. Any other ideas? Yeah.
Take the top 3 best workers and just have them vote.
Yeah. 3 best vote. Very similar to a threshold, but subtly different.
Oh yeah, I don't have to guess what the threshold is.
There's one other thing that you can do here that's slightly more complicated, and that's to actually formulate this as an EM algorithm. How many are familiar with EM algorithms from some intro to machine learning class? Okay, only a few. Basically, the way an EM algorithm works is you have 2 steps in your process, and you alternate between doing those 2 steps. And so here, for this example, the two steps are you alternate between, for a given scoring of each of your labelers, you produce labels, right? So that's step one. And then step two is for a given set of labels that you've predicted, you use those labels to score the workers. And so, for your next set of labels, then you see how all of your workers did on those labels, and you use those weights to give new scores for your labelers, and you alternate between those two. And then eventually this algorithm will converge into something that's slightly better than doing one of these. All right, there's another category of things that we haven't really talked about, which is like how can we get better data? Like how can we go back to our data collection process and do better?
Things that are 3 people agree, you just accept it.
Say it again.
Things where there is 2 out of 3, which is about 20% of the data, you could go back and ask 3 more people.
Yeah. So ask where we disagree. I like that a lot. Other ideas?
You format the question a bit better.
Yeah, I think that's great. Yeah, like what specifically did you see that was not great?
It's pretty open-ended. You just had to write down adjective, you give them a pool to select from.
Yep. Yeah, I was hoping someone would say that because that's definitely something that you can do. Any other ideas?
Specifically, you could split synonyms and antonyms into separate steps so that it's easier, so there's less error.
Yeah, I totally agree. When I was going through and labeling these, that was very painful to keep in my mind the entire time. Another thing you can do is you can use your scores for the labelers, and you can go back, and as you're collecting more data, you could just say, I have some portion of my data set where I know how well the labelers are doing, and so I'm just literally only going to take the labelers that I know are good, and they're just going to be the only ones that are allowed to answer my question. Yeah, so this is just, the purpose of this exercise was just to give you a sense of, this is something that you often actually really have to do in a machine learning organization, and there's a lot of complexity to it, and so I was hoping that we could just kind of get to some of the big ideas about how you can get better labels. Yeah?
I'm sorry, I just missed it. Can you repeat the last part you mentioned?
Last.
For better data.
Yeah, so one other thing that you can do is you can, next time you go and collect data for this task, you can just specify in Mechanical Turk that you only want to accept answers from people that you already know are good labelers based on the scores that you gave them before. Yep.
Can you talk through the EM algorithm?
I don't want to go through the EM algorithm. I'm happy to talk about it after, but just because it's we're running slightly low on time and it's a bit complex. But it's a good thing to read about as well. It's like a good concept to be familiar with because it comes up in a lot of places in machine learning. All right, a couple of references I wanted to mention on getting better labels. There's a couple of papers and a course from UPenn, which I actually modified this project from. Okay, so homework for next week. One note, class is going to be on Thursday next week instead of Wednesday. And there's a lecture to watch, which is the troubleshooting lecture. And in terms of your project, there's going to be 2 things to work on. The first is actually going and collecting an initial version of your data set. So hopefully if it's publicly available data or if it's something you can scrape, then this is pretty easy. And if it's something that you need to collect yourself, then this is going to be an ongoing process, but just get that process started. And then complete a project proposal with your team. And I'll talk about this more in a second. And then once you've done these things, I want to get people in the habit of posting their updates on project updates so that you can start to get feedback from me and the other instructors and your fellow classmates just to kind of help you through this process. All right, project proposals. So why are we asking you to do this? Well, 6 weeks is pretty short to do a project like this. And so the goal is really to make sure that you have picked a project for you and your team that's actually possible to achieve in that amount of time. And then also just, you're going to put some of your ideas there. And so hopefully you can get some feedback on the things you're planning to try and what else you should look into. There's an example proposal that I'll talk about quickly. All right. And so, it's just kind of this is a sample format. You don't have to do it exactly like this, but you should cover the same topics. what project are you working on, who's your team, and then kind of what's the goal of your project. And then we want you to talk about like what data set you're going to use or plan to collect, what baseline you're going to create for that data set. So like, is it, are you using a linear regression, or is there some way of telling whether your model is doing well or not? And then what model architecture and loss function. So like, what are you going to train on that data set? And then finally, like, since this is an applied deep learning class, we want to try to get at what is the end result of this going to look like. Is it like a web app? Is it something that you're deploying on your phone? Is it, is the project too complex to really be able to do that? But like, what is this going to look like? And then lastly, we have a section for, what's the stretch goal of the project? So like, if all of this stuff goes well, what do you hope to achieve on top of it? Any questions on the project proposals? Yeah.
So project proposal is happening after we can form the teams, right?
Yes.
There's going to be like a pitch stage or like finalization cutoff date when we can forming the teams?
Yeah, we're going to finish formulating the teams now, hopefully, and hopefully over the, we'll do our best to do it in the next 10 minutes, and what doesn't happen in the next 10 minutes can happen online in the next couple days. All right, great. So most of you have signed up for a project. Is there anyone who hasn't chosen a project at all yet? Okay, a couple people. But there are a lot of projects that are won. It's okay if you really want to do a project by yourself, but I would prefer to have projects be on teams because it's important to figure out how to work on this stuff as part of a team. And also, there's just a lot of work, and so you're going to need more people to get it done. So what I want to do is, if you're on a team that's already 2 or 3 or 4, and you feel like you're sort of settled as a team, then I want you to go into this kind of like back room and just spend the next 10 minutes meeting with your team, planning, figuring out what you want to put in the project proposal. For everyone else, so if you're not on a team, or if you're on a team of 1, or if you're looking for more people for your team, then just stay here. And the idea is like, hopefully we can start consolidating some of the teams. Yeah. I'll share all the slides after, yeah. Great, yeah, so you have the next 10 minutes. Let's try to get some project teams finalized.